Okay. Oh, thank you. So, my name is Tiago. I'll be presenting alone. Lynn helped me with the slides and Jelko as well, but the presentation is entire me. And so, just to give a little bit introduction here, I'm working with the scheduler with Colin and Andrew here. They are developers on the Telescope Insight team here in Tucson, and Lynn, Owen, and Peter on Seattle on the service strategy team. So we do most of the development on the scheduler part, and Peter and Lynn and Owen help us on the algorithm part of it, which is now the feature-based scheduler that I'm going to show you here today. And so one of the main ideas that we have about the scheduler, one of the main goals that we have for the scheduler is that it's going to be flexible enough to support the input from community, from the science community, and also to support the survey operations for the entire 10 years. So during the 10 years, science goals may change and we may need to adapt the strategy. So we want to be able to provide that flexibility on the scheduler from the beginning. That's one of the main reasons we are exploring this new algorithm, the feature-based scheduler. And I hope it to be clear during the presentation that this flexibility is part of the feature scheduler. So just a little bit of overview on what we're going to talk about here today. So recently, one of the things that we developed on the scheduler that's part of the latest releases, we generalized the code in a way that you can use the scheduler, the LSST schedulers as a whole, with different algorithms. So we developed this interface, we call it the driver API, which is, so basically we have an API and you can develop your own scheduling algorithm, and using this API, connect that to the LSD system. So this was, we started developing this at the beginning of the year. The first releases, 1.2 scheduler already had the API available, even though it was not fully integrated. And now we just the latest release have a fully integrated API. So now it's possible to connect different schedulers in a much cleaner way than when we first started. And together with this new API, we developed the what we call the driver for the feature-based scheduler, and we already had it for the proposal-based scheduler. So now we officially support two schedulers or two scheduler algorithms, the proposal-based scheduler, which is the old scheduler, used for the simulations, as Federico was mentioning, and the new feature-based scheduler, which had its own simulator package. We now integrated it with the LSST simulation package and the LSST scheduler system. So we can use it not only for simulations, but also for operations. So the proposal-based scheduler is the one that we use it for the baseline 2018A. It's the current baseline. We also use the proposal-based scheduler for the simulations for the COUT white papers. And now we have the feature-based scheduler. It was originally a prototype code, and we developed the code to a point where we can now simulate, make a baseline simulation which is compatible with the proposal-based scheduler simulation, and we now have enough knowledge about the system to move forward with this scheduling algorithm. And the good thing about the feature-based scheduler is that it provides much more flexibility to change the observing strategy and implement cadences that are more different from the ones that we can do with the proposal-based scheduler. It's much easier to realize this different types of cadences. And so for the presentation, I basically separated it in three main topics. The main focus here will be the feature-based scheduler, and I will start with a bottom-up overview of the feature-based scheduler, showing how the code is organized, what's part of the code, and how they interact with each other. Then I'm gonna do the same thing again, but now from a top-down approach, where I'm gonna show how we can achieve the new simulation of the baseline candidate baseline with the feature scheduler. So we start with the general overview, and then once you understand what the nomenclatures and the definitions of the feature scheduler, I can show you what we use to make the baseline and how we can improve upon it, how we can implement different kinds of strategies with this new scheduling algorithm. And then I'll finalize with some updates on the scheduler development. I'll show basically the release note on the last scheduler code, and with the main features that's part of this release. So let's start
Tiago?
with the yes.
Sorry, before you get into it, just to give a very, very high level overview of what the scheduler is, as some people are asking online. So basically, what is the scheduler responsible for, and what is it going to be used for? And again, if you can iterate on what scheduler will be responsible for actually scheduling the telescope versus generating the op-sims, and what the differences are.
Okay, so what the scheduler does is it's going to provide targets for the telescope to observe, right? So it has this, we configure it with a set of to come with a cadence strategy, and it gets input from the telescope, from its current state, and then it has to generate a target to observe. Now the scheduler system, on the LST scheduler system, is a set of, we structured it in 3 different packages. One is that the part of the scheduler that communicates with the observatory control system. So that part of the scheduler is responsible for the communication logic. So when the observatory control system, the OCS, wants to start the night, it will talk to this part of the scheduler to configure it and to start the scheduler. And once that part is set up, that's also the part that's responsible for getting the observation from the scheduling algorithm and getting that observation to the OCS. And the OCS performs the observation. So the scheduler is only providing observations or targets to observe, and the OCS, observatory control system, is the one that actually performs the observation. And later, the scheduler gets feedback from the OCS that the observation was completed successfully or not. Then after that level, we have what we call the driver API, which is basically an interface. So we have this control part, then we have an interface where we define how you can connect a scheduling algorithm with the LSST system. And then at the other level, we have the scheduling algorithm. So right now, the old scheduler had the proposal-based scheduling algorithm, which implements kind of a specific algorithm, and now we are developing the feature-based scheduler to basically replace that algorithm and future simulations and operations. So the same system, we can connect to the real OCS. We can also use it to simulate a cadence with the simulated OCS, which we call SOCS. So it's the same system. The same code is connected to both the main observatory control system and to a simulated observatory control system. So it's the same code, the same structure we use for simulations and for operations. So we have confidence that we are developing tools to debug the cadence. We can work it now, and we can work it the same tools later during operations. Does that answer your question?
I think so, yes.
Okay.
Thank you.
Okay. So now let's start with a bottom-up overview. So this overview so what we're going to talk from now on is basically the feature-based scheduler, which is the scheduling algorithm. So I'm not talking about the communication between the observatory control system and the scheduler, and I'm not talking about the interface between that. It's just the algorithm, how we can come up with a cadence strategy or a survey strategy. Okay, so this is going to be about the algorithm we use. And so this is like this image right here is like a tomography of the feature-based scheduler brain. I'll be very brief about this one because we get in details in the next slides. So at the left here, we have the features, and I'll talk about the features soon. In the middle, we have the reward maps. So we get the features are used to compute the reward maps, and then those reward maps, they are combined, and we have a final reward map, and then we select from that reward map, we select the field to observe, right? So now let's go into details. What is a feature? What is in the middle? The reward map is computed using what we call the basis functions, and then the final reward map is computed combining those reward maps from each basis function. So now let's go into details in each one of those. So let's start with the features, which is the bottom part of the logic here. So features, they are basically information. They have information about the state of the system, where the observatory is pointing, or the telescope is pointing, what the dome is doing, how fast the dome can move in one place or another, how fast the telescope can move. We have information about the weather, the scene. So, and we also have information about the survey. So those all information is stored in what we call features. And this is a generalization of what information is for the scheduler. So any information that we want to add to the scheduler, time, or some specific event that the scheduler needs to follow, we have to translate that information into a feature. And a feature is basically a Python class and support all Python classes. So it can be arrays, dictionary, classes, float, an integer, strings. So if it's a Python supported type, you can make a feature out of it. So we separate the features in two different features, the survey features and the condition features. So survey features will store information about the survey. And the conditions feature will store information about the environment, the weather, the sky brightness. So basically telemetry about the environment, right? So if we look back to the tomography of the feature scheduler, the left here, you can see some features. I'm not showing all the features, just some features that are basically Hillpix maps. And at the top, we have what we call the M5 depth. So it's basically the 5 sigma depth of each part of the sky. And you see the gray area there is the area that's not observable. And we have the moon here at the right. We have some planets. And at zenith, you see that the zenith is not computed because it's not observable. The LSST telescope cannot point at zenith because it's an out-as telescope. And I mean, cannot track. You can point, but cannot track. Then after that one, the next one is the number of observations. And here we are tracking the number of observations across the sky. If you look closely, you notice that we have green and some yellows. So basically, we are tracking the observations across the sky in a Hill pixel map. But when we perform an observation with the LSST, we have a field of view that's larger than a Hill pixel map. So we have overlap between neighboring fields. So then at the edges, we get get more observations per se, right? Instead of in the center of the field, you get one observation. At the edges, you get 2, for instance. And after that, we have the slew time. So basically, we are mapping here how long it will take to go from the current position of the telescope to some place in the sky. You see there's this ring on that feature. That's so if we change the altitude of the telescope more than 9 degrees, we have to realign the optics. So that takes 35 seconds. So we have this discontinuity on the slew time map, which is basically when we need to align the optics again. And the last one that we are tracking here, we are showing here, this figure is the moon distance. So it's just computing how far the moon is from the current pointing. And I'm showing here the M5, the slew time, and the moon distance, they are conditions. And the number of observations, they are a survey feature. So just show how, so they're all features, but they they have information about different things. One about the environment and another about the survey itself. All right, so next on the logic, we have the basis functions. So the basis functions, the idea of the basis function is that we will take a set of features and compute rewards. So typically, in most cases, we have a map, a hill pixel map, with some feature, and a basis function will get that map feature and compute a reward map on the same grid, on the same hill pixel grid. And then we are computing the reward to observe a certain part of the sky. But again, it doesn't need to be a map. It can be like a float, or a more complex, a feature can be a more complex data type. And the basis function can translate that data type using some logic into a reward. So in the typical scenario, we have the slew time. We get the slew time, and we apply some mathematical formula, and we translate that from a slew time to reward. So shorter slew times can have higher reward, and longer slew times you have lower reward, which means it's better to go to a higher reward place. And there's also the cases where we get like a string or more complex data types, and we can compute rewards from that. And one of situations that we want basis functions that tell us how to or when to change the filter. So we can store the current filter, the filters that are mounted on the camera, and the time since the last filter change, and we can apply a mathematical formula to tell us if I just change the filter, I don't want to change the filter, but as time progresses, I may want to start giving some reward to change the filter. Okay. So now if we go back to the tomography of the feature scheduler brain, you see here in the middle the reward computed from the previous features. So the M5 depth become M5 reward map, and the number of observations become a target reward map, which means if a region of the sky was observed a number of times, it gets a lower reward compared to regions that are not observed. So the yellow here is high reward, and the green and darker are lower reward. And the same applies for the slew time. And then if you see the moon avoidance region, it's basically the same reward everywhere except when you're close to the moon. What we want to do here is prevent the scheduler from going close to the moon. But notice that we have a reward map. The M5 reward map also has this kind of measured that as well. But we want to apply a larger exclusion zone around the moon. So what we do is that we introduce this moon avoidance map, which basically gives the same reward if you're far away from the moon. And the gray region means that that region is not observable. So it prevents the scheduler, really prevents it in a hard way from going to that regions. And so next on the line, we have the surveys. Now, I know this is not a good name for this particular part of the scheduling algorithm. We're trying to find a better name for the surveys, but it's just the nomenclature that we use in the feature-based scheduler. Don't get too attached to the name here. So basically what the surveys in the feature-based scheduler does is that they combine a set of basis functions. So when we look back here at the brain of the feature scheduler, what we're showing here, this combination of reward maps, is a survey, right? So the survey will combine a set of basis functions and weight for each of those basis functions. And a survey will also contain features. So a basis function has features, and the survey can also have features, and that those features are used for internal logic. So for instance, a survey can be on a specific filter or a combination of filters, and if that filter is not on the camera, you don't want that survey to be scheduled. So we can use that the mounted filters feature on a survey to prevent the survey from scheduling observations of a filter that's not on the camera, that's not mounted on the camera. So and then the survey applies specific decision function, or which means how the survey will select the next observation given a specific reward. So the survey has basis functions, features, and has a decision function. And a survey can return either a single observation or a list of observations. And for example, here we have the greedy survey fields. This is a type of survey. And what this survey does is combine the basis functions, and it will select the highest reward point in the sky. And from that highest reward point in the sky, we select the closest survey field, which is we have a tessellation on the sky from, in this case, the LST camera field of view. And this tessellation will be, one of those pointings on this tessellation will be close to the region of highest reward, and then this survey will select that pointing. And each night, the greedy survey field will randomly deter this tessellation around the sky, so we have nightly dithering. Okay, so this is an example of one of the surveys that we use. Okay, now if we go back to the feature scheduler brain, this map here is a combination of a weighted combination of the reward maps from all the basis functions, and we have the red dot there is centered on the field, the survey field, closest to the point on the sky with the highest reward. Of course, we cannot see it exactly here because of the gridding, but and the pointing is not of the size of the field of view, but just to illustrate how that selection is done. Okay. Now that's not all. We have one other level, higher level on the feature scheduler, which is the core scheduler. Now, the core scheduler is responsible for selecting the next observation. So the core scheduler has a set of surveys. So each survey will return basically a reward and an observation, or a reward and a list of observations. And the core scheduler selects the observation or list of observations with the highest reward, and then builds a queue with proposed observations. If only one observation is proposed by a survey, the core scheduler will send an observation, and then we'll repeat the process. If we have a list of observations from a specific survey, the core scheduler will check with the survey that the observation is okay, and then send that one. And then it repeats until the queue is empty. So one of the things that happens from time to time is that we are in the middle of a deep drilling field. And then, so the deep drilling, there's a deep drilling survey, which gives a list of observations. And in the middle of the sequence, the scene or the cloud gets out of the observing range. So in this case, we need to interrupt the sequence. And the survey has a logic to tell the core scheduler, okay, this observation is out of range, just clear the queue. And then the core scheduler checks that with the survey before proposing the observation. And if the observation is out of the bounds, if the survey tells the core scheduler that the observation is not valid anymore, then the core scheduler clears the queue and starts over, which means it goes to all the surveys and asks for a new observation. So now we can piece all of this together into a logic tree, and we have how the feature-based scheduler is organized. So at the top, we have core scheduler, we have a list of surveys, and each survey has a list of basis functions and features, and each basis functions has a list of features. Okay, so now that we understand how the feature scheduler is structured, let's see from a top-down approach how we can construct a baseline using the feature-based scheduler. So I'm not going to talk about the core scheduler here because the core scheduler is unchanged. We just configure the core scheduler with a set of surveys. So I'll skip the core scheduler and go to the surveys. So the survey that we have right now with the baseline basically is a combination of different, the baseline is a combination of different surveys. So we have one survey for each filter. Now, this is how we are doing it right now. It doesn't mean it has to be done this way. This is how we are implementing, how we are configuring the feature scheduler right now to reproduce a baseline which is similar to the current baseline. Okay, so we have a set of greedy survey fields, surveys, and each of those surveys will make observations on all the footprint. So it combines white fast deep, galactic plane, the south celestial pole, and north ecliptic spur in a single footprint for each filter, right? And so we have one of those surveys for each filter. Then next in line, we have the pair survey. So this is a type of survey that's scripted, as you can see by the name. The pair survey is scripted. And what this survey does, it is gets observation from the greedy surveys and schedules them for pairs. So we can configure them to wait a certain amount of time before starting to propose pairs again. And we have timeouts set. So if the pair is too old to be dropped. And now since we are trying to reproduce the baseline 2018A, we are doing pairs in GRIZ. And this particular survey here will not try to change the filter. So as in the baseline that we have right now, there is no attempt to change the filter between the first and the second observation of a field. So we are following the same prescription, and we're not trying to take pairs in different filters. If the filter changes before the pair start, it's taken a different filter, but if it doesn't, it would stay in the same filter. Now, I'm saying this because we can do it differently, and we already implemented a pair survey script that changed the filter. So we have a specific survey that can, when it's trying to get a pair, will change the filter. So we get pairs in different filters, and we actually have a simulation already with this new pairs in different filters, so can provide the simulation for the community to look into it. Right now, the metrics that we have, they are not mapping any particular aspects of how change the filters improve some metric. So we need that input.
So Tiago, if I may interrupt, I'm not entirely clear yet what a survey is, and also others were asking online. So would it be fair to say that as it is implemented right now, a survey is the footprint for a given filter, and maybe some extra constraints on the requirements on the time between images?
So that's what the survey can be. And the greedy survey definitely is that. So the greedy survey is a footprint with some properties on how to observe that footprint. But like the pairs is something different. A pair will get an observation and try to take it again after some time. And the same for the deep drilling. The deep drilling observation is not a footprint, it's a set of fields that to try to schedule to observe in blocks in different filters in the GRIZY or U-band filters. So a survey is not a good name to use here. I know that, and we understand that. But you can. So a survey tries to implement observing strategy, particular observing strategy. So the greedy survey tries to implement a greedy survey strategy, and then the pairs tries to implement a way of repeating observations. Okay. And the deep drilling observations is also a scripted one, which the idea is that you have a field, you have how much time you want to dedicate to that field, and you try to observe that in optimum conditions. So survey really is how you implement your strategy and how that strategy can be modified using a set of basis functions and features. Okay, so I think it will be clear when we start getting into what is inside each of those surveys. But if it's not clear, I can try to make it clear later. Okay.
No, and just maybe Lynne was also discussing this she's answering some of the questions online, so maybe let me take the chance to say you all may want to also keep an eye on the chat where some questions are being asked and answered live. And that about the survey, one way in which she answered it that made it a bit more intuitive to me is to describe it as a specific survey map, which a reward map essentially, right? So that's essentially what a survey is.
So the survey computes a reward map, but then it makes a decision. The point is the survey object, it's just a Python object that if you call it, it returns a list of observations, and you give it all the observations that have been taken and the current conditions. And so it really, you can put any logic you want in that box. It's just, you give it all the information that's happened, it says, here are the observations I want to take. And so for a lot of the surveys, we're using this Markov decision process with basis functions and maps to make that decision. But for the deep drilling fields, it's very simple logic. It's just some if statements of, is the field up? Have I observed recently? Okay, go, right? So that's a survey that has very simple logic behind it, but the survey object just returns observations that it wants.
That's brilliant. And as you started speaking, Peter, Tom Laredo has said it could be clearer if you tell us what the survey is in Python, which is exactly what you did. So wonderful. And then Rachel has mentioned that she's still a bit confused about how pairs are constructed.
So there are two ways we can do pairs. One is we have a survey that just sits and kind of listens to the incoming observations that have been taken, and it makes a decision that says, oh, that's when I'm going to want to pair later. And it waits until later and it says, oh, here's the pair I want. And so it returns and says, this is the observation I want. And that will complete a pair. The other way we're doing it is, one survey requests kind of a blob of sky, and it does the calculation to say, oh, I can trace this large blob in 30 minutes, and then it just repeats it. And so you can kind of get your pair in a blob, or you listen and say when you want to pair it.
All right, thank you.
Yes.
Thanks.
Okay. So basically these are the surveys that we need for the baseline, and then first we have the deep drillings. We're adding the 4 deep drilling fields. They have to be observed the GRI, ZY in one set, and the U has to be observed in a different time because the U band is only available during dark sky. So that's why we have deep drilling for each field, 2 deep drillings surveys for each field. And so we have the 4 fields and the 5th field that we added just to make sure that we have the number of fields that are planned for the deep drilling. So let's take a look at how we configure the greedy survey fields. So the greedy survey fields that we are using for the baseline right now is a combination of basis functions. Now again, each basis function will provide a map, a reward map. The survey will get each of those rewards and provide a final reward map. So I'm highlighting here those maps that are shown here at the image on the right, the M5, the target, the slew time, and the moon avoidance region. You see that the slew time is called aggressive because I changed it a little bit to be closer to what's on the proposal-based scheduler and named it aggressive. And some of the features, some of the basis functions that are not shown here, the hour angle basis functions basically try to observe close to the meridian using the hour angle bonus. There is a meridian basis function, which is basically as a mask around the meridian. And we have a basis functions to take care of filter changes, the goal restricted filter basis function. So it not only takes the time into consideration, but also the number of observations that you have on each survey, and then the goal that you want for each survey. So if a survey has a certain goal and you have a lot of observations on it, the reward that this basis functions will give is lower than a survey that has a higher goal and lower number of observations. So we also added avoid fast revisits. In some cases, it's not very, it's rare, but we want to avoid them. The observations are repeated not by a pair, but by going back to the same field, because the slew that we give is very small, so it ends up going back to the same field on a fast basis. So to avoid that, we added this basis function that penalizes going back to the same field in a certain time. And so again, this is just, we're trying to reproduce the proposal-based scheduler, and that's why we added some of those basis functions here. Then we have the clouds, which basically, if the cloud is above certain threshold, the survey won't be observable. And the moon avoidance to avoid going too close to the moon. And we also add the mounted filters as a feature, because the U-band is not always on the camera. So when the U-band is not on the camera, the survey with the U-band won't be observable. And this is a decision that the survey takes from that feature. Afterwards, we have the pairs. So the pairs, we add a couple of basis functions so we can take in considerations things like the cloud, avoid the moon, and stay close to the meridian. And we also add some features for the pairs to make decisions. So we have the pair map. So this is a map of the regions of the sky that you want to pair. So if an observation by a greedy survey is done outside the region that you want to pair, the pair survey will ignore it. And then we pass the time, we pass the current filter, and some other features for the pair survey to take decisions. And finally, we have the deep drilling, and you see that the deep drilling is basically features. There is no basis functions on the deep drilling. As Peter mentioned, the deep drilling is just a series of if statements. So those if statements use the information on those features listed here to take a decision. Is it time to make an observation of this deep drilling or not? And you see, for instance, that I'm adding here the cloud, the blue cloud. We also have, so I'm passing here the number of observations. You can see here the number of observations and the number of observations that I have on this survey. And the main reasons that I can, using this information, the number of observations, I can compute which filter needs more observations. And then I can shuffle the filters on the deep drilling, so I can, for instance, start on the filter that I was observing and end on the filter that needs more observation. So this kind of decisions, we can make it easy here on the deep drilling just by passing information to the deep drilling. And I also pass in here at the top the mounted filters. So if the U-band is not on the camera, I won't be observing deep drilling in the U-band. So now, just to illustrate some of the basis functions, I selected 3 different basis functions, one with only conditions features, one with only survey features, and one with both, just to show that the basis functions can be simple enough, and they can also be complicated. So this is the M5 basis functions. We basically pass the condition of how the 5 sigma depth across the sky. And it will return a reward map, which is basically the difference between the 5 sigma depth and the darkest that that position of the sky can be. So very simple basis functions. And the next one, which is the target reward map. So this basis functions will map how many observations you want on a particular part of the sky. So we pass to these basis functions the target map, which is the top, which means which map how much observations we want at each position of the sky. Then as survey features, it will need the number of observations, and that number of observations is basically the number of observations across the sky and the total number of observations that was taken throughout the survey. So the first one is a map of observations, and the second one is a number of observations as a integer number. And it will return a map that is a reward map based on those features. And the final one is basis functions that use both conditions and survey features, which is the basis function that I'm using to map when to change the filter, which is the strict filter basis function here. So you see that the conditions features, we have the current filter, the mounted filter, that's so we can make sure that we're not proposing a filter that's not on the carousel, not on the camera. We use the sun position, so we can promote filter changes when we, at the beginning of the night will be during twilight, and then once the sky is dark enough, we can promote a change in the filter. And the same thing at the end of the night. Once the sky starts to get bright enough, we want to promote the filter change to the Y band, for instance. So this basis functions can take the sun position into account when computing the reward. And then we're also passing the time, which is also a condition. And the survey features that we're passing to these basis functions is the last observation. And well, the important one here is, so we have the last time the filter was changed, the number of observations, and the number of observations overall. And this is the goal part of this basis functions. That's so we can, if this particular survey, if this particular basis functions is part of a survey that has a lot of observations and much more than we wanted it to be, we can tune down the reward. So other survey with needing more observations will have a higher reward. So this is a way of selecting the optimal filter to change when we want to change the filter. And basically this will have a zero reward before the time that you want to start changing the filter. So this is the plot that I'm showing here, is just an example of how the reward evolves over time. So, and you see that this reward will return a number, a float, and it has this behavior over time that we can configure, so we can promote more filter changes or less filter changes as we want. And then there is this linear growth between the range that we set. And then we can combine all this and have our simulation. Now, this is a movie. I hope you can see it. I will play it. I'll start playing it. It's not a movie of the baseline. It's a movie of a simulation that I did a couple of months ago, and just showing how the telescope is pointing and the features are changing over time. You see that from time to time, the dot there, which represents the position of the telescope, will be observed in a gray region. That's when a pair is being taken. And you see that sometimes the telescope goes to a region with high air mass, and that's one of the reasons that I added the hour angle basis function, just to make sure. Now it's on a diptrily, so you see the color of the point changing. That's when I change the filter. And once the diptrily is done, it's going to continue with the grid. There you go. And you see that it started the diptrily sequence with the filter it was, and then it finished on the G filter. Basically, it computes which filter needs more observation, and then it promotes, it puts that filter as the final one on the sequence. And it's gonna end soon. But yeah, you get an idea on how it's working. So that kind of behavior right now is the one that I'm trying to avoid when I use the hour angle bonus. It going way down on the air mass. And now it's done. So now I hope you have an idea of how the feature-based scheduler works. At least you have a movie of it working during a simulation the first night. And I just want to give some updates on the development of the scheduler. And so we officially released version 1.3 of the scheduler. That's the one that has the API fully integrated and supports the feature-based scheduler algorithm in a seamless way, and also supports other scheduling algorithms if someone wants to implement them using the LSST framework. And we also implemented a couple of features, and I'm talking about software features, not features in the feature scheduler, but the capability of doing cold start. So this is needed during operations. If we have an interruption and we need to restart the scheduler, we can take the list of observations and replay the observations on the scheduler and review the state of the scheduler from that list. We also implemented the improvements on the control sequence. The previous scheduler was using a control sequence that was not compatible with the design of the LSST control system. So we improved that and make it slightly closer to what we need. It's not ready yet, but we are moving toward having this interface ready for operations. We implemented DOM crawling. That's one of the things that we're missing on the observatory model. We need to implement it so we can get a more precise sleep times from the observatory model. We also added Jupyter notebook integration. So now you can open a notebook and make a configuration for your scheduler using the feature-based scheduler on the notebook and make a short simulation and check the state of the scheduler at the end. And this is very helpful when we're trying to implement some new strategy like pairs and different filters or something more complicated like triples. It's very useful to have a notebook to do that very easily. And we finally have a feature-based scheduler candidate baseline now that we are hopefully ready to make it the baseline soon. So just to finalize here some conclusions. So the feature-based scheduler now provides a much more flexible framework to develop survey observations. We have much more control on how we can implement some cadences. So we have information about the survey and the environment is stored on features, and those features are used by basis functions and the survey to compute rewards and take decisions. We can implement complex behavior using basically so the features and the basis functions, they are basically Python classes. So it's easy to implement complex both spatial and time-dependent behaviors. And the feature-based scheduler code now is mature enough that we are able to provide a baseline candidate that's we can compare directly with the previous baseline. And so one of the things, we had a lot of issues that when we started doing that, like observations taken too close to the moon or observations taken at the wrong scene or cloud conditions. And we could implement all those features per se on the feature scheduler to map all those requirements. And now we can actually replicate the baseline that's compatible with the old baseline, and we improve upon it. So we fixed some issues that we knew we had with the previous baseline, with the proposal-based baseline. We're fixed on this baseline of the feature scheduler. And just some support material for those interested. We have some instructions on how to set up and run Opsin Docker container. So Owen prepared these instructions for the hackathon that happened last week. You can follow this link here to show you how you have to install Docker on your computer, and then you can download the container, and it's easy enough to set it up. And Owen's showing here how to change the configuration, how to play with the scheduler, and I think it shows how to open it on a notebook, but I'm not sure. I have to check that. Some material on the feature scheduler. We have this paper from Elahi. There's a new paper coming pretty soon with more details. We have the baseline candidate with the metrics for the baseline candidate available online, and we have a comparison of this feature-based scheduler candidate with the current proposal-based scheduler baseline. And well, thank you very much.
Thank you. Thank you so much. This was great. So if you have not followed on the chat, so we only have a couple of minutes left for questions, but I guess a lot of you were active online asking questions, and Lynne kept track of them very thoroughly and answered most of them. If you have a pressing need of having the question that you asked online being asked live in the video, just let me know on the chat and I will ask. Otherwise, anybody that was not asking questions on the chat has any questions at this time.
Yeah, I have one. It's Phil here. So what you showed was it seemed to be mainly a sort of greedy algorithm, always taking the highest reward. Have you experimented with doing some sort of annealing, randomly taking a low reward, pointing, every now and again, which might, I don't know, free up the scheduler later?
That particular strategy we haven't tried, but Peter have been experimenting with blob scheduling, which is it starts from greedy, but then it implements a scripted sequence later. Is that right, Peter? But though that kind of experiment it's easy enough to do with the feature schedule that we could easily implement it if wanted, or it's easy enough that someone can implement it. Did I answer your question?
Yeah, I think so. I heard that you haven't tried introducing randomness yet, but the code is flexible enough to be able to support such experiments.
Yes.
Anybody else?
Nope.
Wonderful. Thank you, Tiago. Thank you very much. Stay tuned, Science Collaboration Chairs and PTS, for the schedule for the next few meetings. Jelko and I have been chatting about it, so I will send some dates and topics as time in a couple of days to fill in the next few months. Remember that if you have something that you want to ask, I'm going to copy the spreadsheet. Anyone with the link can view. No, anyone with the link can edit. I'm going to copy here the spreadsheet. The Google form with which you can request a topic for discussion, and that goes on a spreadsheet. And I will also distribute again the spreadsheet online, so on the Slack, so people can consult the topics that have been proposed in the next few, to be discussed in the next few meetings, and propose others if you see any gaps. Otherwise, thanks again, Tiago. Thanks, Lynne and Peter, for contributing and answering the many, many questions. The questions have been transcribed live by Phil on the Google Doc. The Google Doc will be shared again as a link on Slack. So will the video and the slides. Thank you very much.
Well, thank you.